For this last and final chapter video in chapter 8, where we're going to discuss retrosynthetic analysis to be able to design a synthesis of complex molecules. But before we get to that, let's think about some potential pitfalls that come up in the course of synthesizing a molecule. Let's say that you want to make this molecule really bad. Okay. One, two. Yep. Let's say you really need this molecule. Okay. I don't know why. Maybe because this is like the new miracle drug structure or something that cures everything, perhaps. But and then let's say you have in your lab this molecule. So you think, well, if I could just add this ethyl group as a Grignard reagent into this ketone to make this tertiary alcohol just like we did earlier, then we should be able to make that molecule. Well, that's kind of a understandable, idea, strategy, but it turns out this would never work. Now, why is that? Let's think about this. So, right, the difference between this substrate and this substrate or starting material is that this molecule has an alcohol in addition to ketone in it. And what's wrong with that? Well, remember, alcohol is somewhat acidic. Right, that's why we said it's amphoteric. Right, alcohol is an amphoteric functional group. And remember, the Grignard reagent is very much a strong base. This kind of dissociates into the magnesium cation and a ethyl anion. Right, and this is a very strong base, which means you would pick up this proton very easily. And what would happen? Well, you would get this alkoxide, and this ethyl group would pick up a proton, and I hope it makes sense to you. It becomes ethane. Right, like this carbon had an anion, and then now it picked up a proton. I hope that makes sense. And an ethane, it turns out, is just a gas at room temperature. So we say, in chemistry, we would say that ethane gas would be evolving. In chemistry, the word evolution means a gas molecule is formed during a reaction and then flies away. That's called evolution. Okay. So some caveats to remember: acid-base reaction like this, or any acid-base reaction, very fast. Okay, so that's usually the first thing that happens before any other reaction can happen. And organometallic reagents are very strong bases. Okay. So they'll be protonated by any hydrogen on a heteroatom. Oh no. Sorry, my daughter said something, so I responded. Now, with that, let's think about. So the takeaway here, right? Like some reactions that you might plan might not work. You just have to pay attention to like what's all in the molecule, because the chemicals don't know that that's the molecule you want to make. Then this is the molecules they would actually make. Okay, so now let's think about designing synthesis, how to make molecules, especially complex molecules. We're planning a multi-step synthesis. Complex molecules would probably take many steps to make. So how do you do multi-step synthesis planning? And to do this well, we have to do we should take an approach called retrosynthetic analysis. And unlike the sort of colloquial use of the word retro doesn't mean like old. Retro just means backwards. Okay, I'm sure you guys know that meme that I'm referring to. So we have to think, sort of walk backwards to do a good planning here. And so what is retrosynthetic analysis? Kind of in a abstract sort of big picture view, you start with the target that you want to synthesize. Maybe the target is the complex molecule that you want to make, and then you walk your way backwards to the starting material. Typically in chemistry we think of starting material and then we think about the product, right? That's the forward thinking. You want to think backwards to design a synthesis. That's the point. If you start back from a complex target, right, maybe this could be formed by two different less complex molecules. And then combine them together. Right, and then that now each of these could be made from perhaps like a slightly less complex molecule. And then if you go all the way back to if you go way back, maybe you could trace your way back to simple starting material. And these have to be commercially available for you to actually do the experiment from like a chemical company, right? Otherwise you're not gonna be able to have it if you can't buy it to make this a little more complex molecule, and then eventually you get to the target. Now these arrows actually mean something specific in organic chemistry, and this means can be made from. And that's what this is called a retrosynthetic arrow. Maybe I should write that here. Okay, and so you break that complex target molecule down to simpler and simpler molecule until you get back to simple starting material that you can buy. That's the idea. This process is also often called dissecting a molecule. Okay, so what would that look like? The retrosynthetic analysis. Let's say your goal is to make this, so that's your target. Okay, so the target is this guy. Okay, and you wanna, but you could only buy these starting materials from the chemical company you work with, let's say. So how do you do that? You start with the target. You don't start planning of the synthesis from the starting material where you start, then it's really hard to come up with a good synthesis. Okay. So you start with the target, and you pay attention to the functional group present, namely in this case the alcohol. In this chapter we talked about how to make alcohol. Do we know how to do that, right? For instance, you could add a Grignard reagent to a ketone to make that. So we could dissect this molecule perhaps at this bond. So then this molecule can be made from, here's the retrosynthetic arrow, this Grignard, some kind of halide, plus if you had this ketone. Right. Now, how do you make the ketone? You could make the ketone from the corresponding alcohol, where this is the alcohol, right? So we could say this could be made from right, and now that alcohol can be made from some sort of Grignard as well. So this could be made from some kind of alkyl halide like that, and then eventually we could make the aldehyde from this, and then that aldehyde could make this alcohol through addition of Grignard derived from that. So that's our retrosynthetic analysis. Notice we started from the target and worked our way backward. That's how you should think about synthesis. Okay. Now, how do you do this in real life? Well, so first, now that we finished the retrosynthetic analysis, this is we're going to think about the forward synthesis, how we would actually do this step by step. Now, to first make this alkyl halide, we have to use chemistry that we skipped over and didn't learn in chapter 3. I'm going to introduce you to it, but I don't expect you to know the mechanism or why it works or anything like that. But so for now, you just have to know that when you treat alkane with bromine, and this symbol just means H nu means the energy of the light, Planck's constant times the frequency. So that's just another way of saying this is light energy. If you shine light on bromine with alkane, you get bromination reaction. Okay, so that's just something I want you to know. And also this bromination happens at the most substituted carbon, as in on this substrate it doesn't really matter because it's all equivalent, all 5 carbons. But now this is something we could work with. If you treat that with magnesium in ether, right, you can make the Grignard reagent, right? Now, so that's the Grignard reagent we need to make this secondary alcohol. Now, to make the carbonyl compound that you need for that from the starting material, well, 1, 2, 3, 4. I think I was missing a carbon there. This needs to become aldehyde. We know how to do that. By the way, it might be a good exercise for you to pause the video to see if you could come up with the reagent to do these reactions with. So you should be review. So that would get you the aldehyde, and if you mix in that Grignard reagent, in ether or something. By the way, the semicolon in organic chemistry means then, so this is one step, and then as a separate step we're gonna do acidic workup. This semicolon means the world here, because if you added this with the Grignard, you would just quench the Grignard and it would not work. So without that semicolon, this is incorrect. It would not work at all, right? And then that would give us that product. I hope that makes sense. Now, from here, now we want to think about the synthesis of that. What needs to happen? Oxidation. So this could be either done by PCC in dichloromethane, or chromic acid made from dichromate and sulfuric acid. Either would do that because it's a secondary alcohol, right? And then finally, if this gets treated by phenyl Grignard, that's abbreviation for this guy, perhaps with the bromine, and then followed by acidic aqueous workup, that will give us the product that we are after, right? So that's a 1, 2, 3, 4, 5, 6 step synthesis, but we were able to design it because of the retrosynthetic analysis. And of course, this is one of those things that you have to practice a lot to get good at. And for the rest of the semester and for the rest of the year, really, we're gonna try to shift our focus, or we're going to try to have additional focus in our class, which is coming up with synthesis of molecules. Because if you're going to be an organic chemist, which I realize not everybody here is going to be, but the goal is that at the end of the year, you're going to be some sort of an organic chemist because you finished the whole year of organic chemistry. You need to be able to design and think about how to make molecules. And that's an exciting idea because if you get good at this, you could build any molecule you want. You could be this small, you could be an architect, engineer of the smallest building, smallest objects that we can manipulate. And that's going to have a molecular impact on whatever it is you want to apply it to, oftentimes biology and medicine.